session on foundations and deep excavation, which will start from 4:30 p.m. to 6:30 p.m. And the thematic lecture will be delivered by Professor Ramanathan Ayothiraman, and this session will be chaired by Professor Sirish Saride and Professor Said Kajamullah. Over to you, sir.
Hello, myself Dr. Syed K.K. Hosseini. I am co-chairing this session on foundations and deep excavation. In this series, first we have a thematic lecture by Professor Ramanathan, and the topic of his presentation will be influence of deep excavation and foundation loading on the response of the existing underground metro tunnel in cohesionless soil deposits. Okay, so Professor Ramanathan is currently working as a professor in the Department of Civil and Environmental Engineering at IIT Tirupati since December 2024. And prior to this, he worked as a professor. He worked as a faculty at IIT Delhi for about 16 years and at IIT Guwahati as well for 4 years. And he has got his degree, Bachelor of Engineering in Civil Engineering in the year 1998, and then ME in Soil Mechanics and Foundation Engineering in the year 2000, and he's a gold medalist in his MTech program from CEG, and his PhD is in the topic of soil dynamics in the year 2005 from IIT Madras. Professor Ramanathan has published about 135 papers in journals and conferences, and he is currently serving as a member of BIS for revising the various codes related to soils and foundations, machine foundations, and rock mechanics. And Sir has completed about 100 sponsored research and consultancy projects of value more than 25 crores. Over to you, Professor.
Thank you. A very good afternoon, and thank you. And I'm very sorry for loading the file in the last minute. Yeah, so today I'm going to talk about influence of deep excavation and foundation loading on the response of existing tunnels in various soil conditions that we have studied. But today I'll be focusing on cohesionless soil, how they behave. And I thank my students Vinay Kumar Singh and Dr. Sumit Mahajan, and their work I am presenting it today. My presentation will be, having a brief introduction and then why this problem is needed, a need for the present study, and then how the details of the study that we have carried out that includes both a comprehensive model experiments in the laboratory and then a numerical parametric study. Finally, the brief conclusion that we arrived at that will be presented here. Coming to introduction, we all know that the major mode of transportation in urban is the roads, and then recently a lot of metro rails are also being used actually. And we know that the metro rail in urban is classified into different terminology, but yes, all of them are important. The major problem with road transportation in urban area, safety is the issue. The kind of traffic volume is increasing, and big traffic congestion is there, and of course, in severe flood conditions, we have this kind of scenario that is coming. So road traffic has significant challenges for us actually. And a lot of metro rail projects, initiative has been taken in India. And if you look at globally also, the running kilometer length of the metro has been given. India is currently third, and with the kind of metro projects being projected and running in another 23 cities, it is going to be the second largest metro network in the country in the coming 3 to 4 years actually. So we are currently having operational length of about 1035 kilometers. And this is the detail showing which are the cities and what are the running kilometers. And I think again table showing how much is the operational, how much is under construction, how much is approved and proposed new routes also. We know that every budget by Indian ministry is actually having a significant budget actually allocated for the transportation infrastructure that includes the metro project construction. So this table shows, all the metro work that are being planned in the Indian different cities actually. And typically the metro projects has, two components, structure, either elevated or underground actually. Okay. Our lecture today is going to focus on the underground portion. It shows what is the comparison of different aspects with respect to elevated and underground metro. Construction method is much, faster in terms of the viaduct, and whereas TBM cut and cover, lot of challenges, and cost-wise, definitely underground tunnel is going to be much expensive than elevated. So the most preferred is elevated, provided the space is available along the road and we are able to connect all the destination that we are looking at with the possibly, elevated metro. But many a times kind of different geographical location that we would like to develop connectivity, it is not possible to go by elevated because already existing density of the building population is going to be much larger. So the only way is to go by underground. So that is the, if other options are ruled out, then we go for the underground metro option. Advantages, no need to say, in densely populated buildings and you want to protect the heritage structures, in all those cases when there is no space available for you to go for an elevated, corridor, then we go for an underground metro. And this is the geological condition that the underground metro is experiencing through in Indian regions. Many sites were soil and some sites were rock, even hard rock. Wide range of geological conditions, it is actually going through. So what is the problem which we are going to address? So basically this underground tunnel construction involves two problems. The first problem is, their effect of tunneling induced excavation on the existing structure. So that is the important problem to be addressed, and I think we have quite a bit of work have been already executed. Guidelines are available in terms of different country codal provisions. Even Professor Loganathan has established guidelines available, textbooks available to evaluate the safety of the existing building due to tunneling induced excavation or deformation. So we have, whether it is a shallow foundation, deep foundation, for both of them, the assessing the safety of the existing building due to tunneling is actually available, and many of the metro projects in fact actually execute that, and they identify the conditions of the building before excavation. Then during the excavation they monitor it, and then they have also the backup plans in case the monitored deformations and the stresses are actually alarming. So this is being followed as a regular routine practice. But what would happen if these tunnels are constructed already and they becomes an attraction point for the future development? And a lot of new development comes close to this actually, existing tunnel alignment, definitely. So then what will happen to the safety of this existing tunnel? This problem was not actually extensively studied. We started this work way back in 2010, and the last 15 years we have been extensively working on this. Some of the findings, I am going to present it today. So our problem is, what is the effect of new construction or new excavation activity close to an existing tunnel, and then how the tunnel will behave, and how do we ensure that these existing tunnels are safe. And as I said, the first category of the problem, when you do the tunneling, what will happen to the pile foundation, how they will deform, these guidelines are already available. But challenges, this has been observed that a lot of damage to the existing structures happens, and which is being taken care. Even in actually India, Calcutta Metro also 2019, there were some damages happened due to tunnel-induced excavation. So this problem still being researched because the existing guidelines, continue to evolve as we experience more and more failures. We learn from the failures, help us to improvise the guidelines and the monitoring mechanism. So this is just to tell you how, when the new excavation happens, the existing tunnel will move towards the excavation actually. On the contrast, when you start constructing the new building with basement, then the movement of the tunnel is going to be in the opposite direction. So that means there is a strain reversal and the stress reversals will happen. And the kind of strain that the tunnel lining will experience, in some loading it will be in compression nature, in another loading condition it will be tensile in nature, and which need to be understood, because the tunnel concrete lining, if it develops some tensile strain beyond the permissible limit, they will start developing crack. And these cracks are actually going to propagate with time, and the long-term durability of the lining is going to be affected in underground water conditions and submerged conditions. And such failures are also reported on the tunnel lining, and these are some of the case studies that are reporting the lining distress or the dislocation or the crack developed at the junction, and due to the new construction activity, and which is the attention which we want to do actually. Yes, as I said, basically the traffic land availability is a big issue, therefore this we are going for that. And typically even raft foundation, typically shallow foundation is not likely to produce a pressure bulb deeper. And the tunnels are generally about 18-20 meter deep. That's a minimum for a single alignment, unless the two lines are crossing where the second line may go to a deeper depth of 30-35 meter. But then shallow foundation pressure bulb is very confined to a shallow. But these days the basement is actually, we are increasing. We are actually utilizing the underground basement space. In India, the 5 basements have been already constructed in Ahmedabad. We can understand now how deep we are going for the basement. And also when 2 metro lines intersect, then we require a depth of excavation of the order of 40 meter. So then definitely they are going to interact with the nearby existing tunnel actually. So therefore the relevance is very important to investigate, and what we did in this study is, so up to 3 basement we have considered, which is most common. 5 basement is very rare, unusual, which can be carried out as a site specific study. The effect of 3 basement excavation and up to a story of 20-story building, which is the tallest building, is normally constructed around Delhi, because we initially considered Delhi region as a study region. Of course, this can be further extended for cities like Mumbai, where number of stories really go much taller. And these are the different parameters that we have varied. The horizontal offset distance between the proposed construction of raft foundation and the tunnel lining, and also the magnitude of loading that we have varied, and the depth of tunnel, a different cover depth of varied, because between the elevated and underground they will transit. The transition zone, the tunnel will be of shallow depth also. So in order to cater to that, we have varied the depth of tunnel as well, and the depth of foundations were varied. So different size of the raft foundation and the orientation of the foundation. A very comprehensive numerical analysis were carried out. But in experiment we could only do very limited study, because the geotechnical model testing would involve a lot of effort actually. So we have varied the effect of water table also in our experimental study. And concrete stiffness would be too strong to show any strain in the model experiment. We need to scale it down, and we have scaled it down to another material, flexible material called HDPE pipe actually as a tunnel. And of course scaling laws were employed to see the same flexibility ratio in the field, and as well as the model is simulated actually. And 2 soil conditions are very predominant in Delhi region. One is Yamuna sand close to Trans-Yamuna river region, and in the other part of the region, western and southern Delhi silt is there. So wide range of soil condition we have counted for that. And we have done the characterization of this basic soil, and scaling laws, as I have mentioned, actually been followed. And this is the property of the HDPE model tunnel that we have used, and of course the steel that I have used. And to simulate the basement raft cum retaining wall, in the field it would be RCC, but we have scaled it down to a steel one, and this is the basement raft and the retaining wall, which we fabricated it integratedly. In the field also, your raft cum retaining wall, they will be monolithic. The same thing we had simulated. And for carrying out an excavation, we need a sheet pile wall. And we have also designed this sheet pile wall based on the prototype 3 basement depth of 12 meter. And then after scaling, we have arrived at the thickness and everything. And only thing in the field 3 basement, you will be using strut and other stuff. Anchored sheet pile wall would be used actually. But in model test, confining stress is very low, very smaller depth. That was not required. With the cantilever sheet pile wall itself, we are able to do an excavation. And this is the sheet pile wall that was fabricated to simulate 2 basement and 3 basement. This is the model setup that we had use a test tank of about 1.2 meter by 1.2 meter by 1.5 meter height, was used, and soil were this is the model tunnel lining that we have used instrumentations to measure the strain in the longitudinal as well as circumferential direction we had measured. And a data logger was used, 48 channel data logger from HVM, Germany. And the excavation was done by a tunnel excavation system which was designed in-house and fabricated, and using the hydraulic jack which is placed horizontally that will push the sampler into the tunnel to remove the excavation of the soil within the tunnel. We have done that. This is the one. And the extension rod can be connected to reach a deeper horizontal length of excavation inside the tunnel. The soil bed has to be prepared at a particular density, and we have taken a 60% relative density that is predominantly available around Delhi region. And in order to prepare that, we had a calibrated method, a plate vibrator method was used to compact the soil, and we have verified by several trials, repeatability was checked. We were able to achieve about 55 to 60% relative density. And this is the way yeah. Okay, sure. Almost done. This is the way the soil bed was prepared. A pre-filled tunnel lining was placed, and then subsequently the other layers were placed. Then the tunneling was done through the excavation system. Then the soil excavation within the sheet pile was done. Then we have lowered the retaining wall with basement. Then subsequently building loads were applied. So this is the way it was simulated. Their construction stages are mentioned here. And we have monitored the strain which are presented here. We can see the first stage, excavation number 2 that is excavation stage, and subsequently the other stage, include the increasing the loading phases of the additional floors. And what is the observation that we had is the longitudinal strain is relatively smaller compared to the circumferential strain, because your tunnel is running longitudinally and you are excavating in a specific layout of raft. So more effect is on the circumferential direction rather than in the longitudinal direction. And the tensile strain were generated in the ground during the excavation, and the opposite in the springing level. But when you go for the loading, the strain direction changes, whereas the crown were experiencing compressive strain and the springing levels experiencing. So that means there is a strain reversal. If you know that kind of cyclic strain happened, then under fatigue, then the concrete is more vulnerable for fracture, cracking actually. These cracks may not cause significant collapse, instantaneous collapse, but what happens is with time, when moisture ingress happen in the submerged condition, it will also deteriorate the reinforcement bar in the lining. The long-term stability is going to be affected, and one fine day if you do not monitor this, all of a sudden collapse may occur actually. So therefore, when we do any new construction, it is important to monitor at critical locations, and in order to identify critical locations, our finding would be helpful to where to place the sensors to monitor during the new construction operations. In fact, some of the cases the permissible strains were exceeded. 150 micron is a permissible strain, and in some construction cases we found that it is exceeding the permissible limits. We done, as I mentioned, comprehensive numerical studies. I'll just show the comparison, but the observation and conclusion is that you can see how the excavation stage, the movement arrow direction shows they are moving towards the excavation, and when you do the loading, structural loading, the strain direction completely changes. You can see the ovaling happening in the opposite direction. And from this different stages and different critical distance parametric study what we have done, and we have found that 2.5 times the tunnel diameter, if this is the tunnel alignment, your new construction has to be 2.5 times the tunnel diameter away from it, if at all we don't want to have any effect. For example, the tunnel diameters are 6 meter, typically what is the metro tunnel dimension. Now you can understand it is going to be 18 meter away from the face of the tunnel, you should not do any activity. But most of the activities will happen within that only. So therefore, what is that alternative way? That means we may have to restrict the number of stories. Like you see, the airport authority coming up and putting a restriction. I have an airport, there is a flying height restriction. You cannot build taller building beyond that. Like that, the metro authorities have to come up with guidelines that this is the number of story that maximum you can build it so that my tunnel is safe. So that is the guideline towards with which we are actually working to achieve that. And to conclude, as I mentioned, this is the critical distance, but we are now working on to develop a guideline to say that if the distance is, let us say, 1D, then what should be the number of story that maximum I can construct. And during the construction, excavation and loading, there is a strain reversal happening. What are the critical locations? Up to what length from the building construction location I should monitor? Those guidelines we are coming up with, and definitely I believe that is going to be helpful. Now we are also working on clay soil condition, because for example, Kochi Metro, Chennai Metro, they experience a lot of clay soil conditions, and one student has submitted his PhD thesis on clay soil condition as well. Once we complete all comprehensive ground conditions and number of floor loading conditions, the final guideline, I believe, is going to be very much useful to the entire country, and they can actually use them to have a safe tunnel performance during the operations. So with this, I thank the organizers for giving me this opportunity. Thank you very much, and I would be happy to discuss if the questions are allowed by our colleagues. Thank you. Thank you very much.
Thank you, Abraham. I think it's late, but at least one question. If you, yeah, I think it's like.
Excellent presentation, Professor Raman. Just one question about your experimental setup. How did you confine your tunnel length? So it is a limited length.
Yeah.
That is not resembling the actual longitudinal section of the
Yes,
field
yes,
section.
yes.
So whether you imposed any boundary condition in the experimental study?
That's a good question. What we have done before going for experimental setup design, we know that that boundary effect has to be understood actually. We did initially a three-dimensional numerical analysis to understand in 3D effect of raft loading, what would be the effect in the longitudinal direction. And so that there is no boundary effect from the tank wall comes. So that is the way the length of the tank was arrived at actually. So we have done that, yes.
Thank you.
Thank you.
Further questions can be discussed a little later.
Yeah.
Thank you so much.
Sure, thank you, thank you.
I think there is, sorry for my late presence again, I was stuck in another TC 307 workshop. I was presenting there is a change, there is a slight change in the order of presentation. Yeah. So we'll go with the last but one presentation as our first one because I have to catch it. So I request Mr. John Gandhi, in search of alternate solutions for big structures at his school. I hope it is okay with other devices. I think it's fine. I think they're all okay.
Good afternoon, and thank you for the organizer giving us an early slot. So this is the bridge we constructed in Wasco. So this was a quite complex one and almost 7.5 kilometer elevated and partly on the grade.
Next.
So this is connecting Varnapuri to Sada. This is around 5.2 kilometer. And connecting to gate number 1, that is within the port loop number 2, Ravindra Bhavan to 2.3 kilometer. Yeah, next. See, this is initially even a tender as well as our beginning. We thought of doing the only pile foundation. But when we conducted, so then we converted almost 50% to the open foundation. And this is quite economical. There's a reason we went for the open foundation. Next. Yeah, some videos we can show.
video.
Any video you
Minute,
can see.
minute. Move on. Oh, video is there.
No?
इसे तेजी से निकाल देते हैं फास्ट
Sir, you have 7 minutes.
ओके
We'll cut it short. We'll cut it short.
yes. Yes sir, अब अपना पीपीटी करते हैं.
See how we cut it short as per you. So this is the typical bridge. Why it is important is, this is a 180-degree curve. And what we have fixed is 48 cables. This is other than geotechnical, I am giving information. All the 48 cables are in 48 planes. So not a single, because it is a curved. So Dr. Kulkarni, unfortunately, he is not there due to his personal issues, but he designed all these foundations. And for this bridge, we got many awards for this. Even Mr. Gadkari said most complex bridge, and it is a 3-stage. One is a railways, and over that there is a road, and over that this is a bridge, 3rd stage. Okay. So I request Mr. Vinay
Yes.
to continue with the geotechnical.
Good afternoon.
Thank you.
Good afternoon. And as sir already to inform that in the tender stage, all the foundation was pile foundation, but during investigation we changed the proposal, and based on our geotechnical investigation, means we have done some boreholes, and the data give us confidence to change pile foundation to open foundation. We have conducted for verification of the loading bearing capacity. We have done plate load test, CBR and DCPT test. This is geotechnical data. SPT in that area 35 to 50 value, and angle of friction 31 to 41. Unit weight 19 kilonewton per cubic meter. We have done plate load test. That plate size was 450 into 450, and hydraulic jack capacity 100 ton and load transfer 32 ton. Based on the permissible plate settlement is considered 25 mm, and allowable bearing capacity at 79 ton per meter square. This is LT. After the total permissible settlement permission as per IRC 78 is 75, but we get 63.75 mm for the span of 25.5 meter, and loading 50 ton per meter square initially. SVC is estimated about 199.6 ton per meter square. The design load was 50 ton per meter square. This is dynamic cone penetration test, and field CBR also conducted, and CBR value is noted as 100% for such a small deformation of 0.75 mm. Only one location we get CBR value is 67%. Based on field CBR, its modulus of elasticity estimated by 42,000 ton per meter square, and bearing capacity also was also calculated from this formula. with the footing width is 0.45 meter and density 1.9 ton per meter square. The bearing capacity factor plate load test as 369, angle of friction was 46 degree, allowable bearing pressure was 50 ton per meter square, model of elasticity calculated 30 ton per meter square, and it is best we have changed the about 42 locations. On the basis of all this design parameters confirmation, we have changed the 82 locations from pile to open foundation and save the timing and costing also. Yeah, thank you. Any question?
Yeah, thank you so much for taking the time.
Yeah.
We have
Thank you. Any?
small and your foundation was
No, actually, first we have done borehole data where SPT and UCS values are give us confidence to change the foundation design, pile foundation to open foundation. After that, we verify plate load test, CBR, DCPT. On all this basis, we have changed the foundation type. Not only one factor, we have checked all the factors, field parameters, and finally we change this design. And we have to submit these reports to government and all these things and get the approval on basis of data.
Yeah,
Thank
very
you.
nice presentation. And I have one follow-up question. I think it's a right question. Because it would have been ideal, or at least to compare the data, you could have shown a board log data of those, foundations, deep foundations versus shallow foundations, because you're talking about SPT numbers up to 50. It's very good strata. But in this locality, we already know that 3 to 4 meters is a hard strata, and below that you have very soft material, shady soil or something you call it, right? Would laterite, yeah. So is there any challenge that you see, or is it something your pressure distribution is? Yeah, maybe. Very well, very well. I hope you have taken care of
Yes,
those
sir.
conditions.
Yes, sir. This bridge is already in operation.
I know,
sir.
I know.
Yeah.
There is no doubt about it, but just for a geotechnical point of view,
Going to the port. So all these heavy loads are being
taken. Yeah, thank you so much.
Thank
Yeah.
you, sir.
So with that, we have one more out of the loop, presentation by Mr. Mustaq. Miss Mustaq. Yeah, assessment of vertical anchor stability in unsaturated sandy soils. Title is very interesting. Unsaturated sandy soil. He's unheard of, so let's listen.
Okay, so hi, good afternoon everyone. My name is Mansha. I am currently a post-PhD fellow in the Department of Civil Engineering at IIT Kanpur. So the topic of my today's presentation is assessment of vertical anchor stability in unsaturated sandy soil. This is the outline that I will follow. And starting with the motivation, so anchors are used for a variety of purposes. But in field the soil is mostly unsaturated, so the analysis based on saturated soil that can turn out to be over conservative and uneconomic. So to consider this, we have to consider the unsaturated soil mechanics, which is done by considering the effect of matrix suction in the analysis, and it will make our analysis more realistic for the stability analysis. Next, the introduction. So the aim is to do the plane strain stability analysis of vertical plate anchors in unsaturated soil, and while doing that, the constant aim was to add enhancing the resilience, safety, and cost effectiveness of our designs. So the objective is to develop numerical solution framework and do a comprehensive parametric study of various parameters. Some of the key contributions from this work were that we have proposed a finite element limit analysis based numerical model which incorporates matrix suction. And we have proposed some design charts which can be used by the engineers in the field directly. Next, the methodology. So I have used the lower bound finite element limit analysis. So it includes various constraints which are the element equilibrium, the statically admissible discontinuities, the boundary conditions, and the yield criterion. These are all the constraint matrices. Then there is the objective function. All the constraint matrices, they are assembled, and finally an optimization is performed on the objective function to obtain the total collapse load. So the yield criterion, we have used the modified Mohr-Coulomb yield criterion. The figure here, it shows the stress state for the Mohr-Coulomb yield criterion, the modified one. So we can see that as the suction increases, the failure envelope, it shifts higher and higher, which means that in case of unsaturated soils, the shear strength will be higher compared to the unsaturated soils. And this sigma is the term here, it is called the suction stress, and the equation was for this was presented by Liu et al. In 2010. The first figure shows the vertical plate anchor embedded at a certain depth from the ground surface, and the second figure shows the typical finite element mesh which was used for this problem. PU is the failure load in terms of which the design charts were presented. Next, the validation. So, a comparison of the present results with those published in the literature for dry sands were presented here, and it can be seen that the present results agree quite well with those in the literature. Next, the parameters involved. A thorough parametric study for a wide range of parameters and a lot of parameters was done. These are some of the parameters that were considered in the analysis. Coming to the results, these two figures show the variation of the suction stress and the unit weight as we go above the water table. So from the first figure we can see that the suction stress, it does not change much with the change in the flow conditions. That is for evaporation, no flow and infiltration, all these lines are merging each other. They're just one over another in case of sands. So from this we can see that the effect of suction stress in case of sands, the effect of the flow conditions on the suction stress in case of sand is negligible. And will be seen in the future results, like these are some of the design charts that were presented. These show the variation of the collapse load, the pull-out load under different flow conditions and different parameters which were the embedment depth, the angle of internal friction of sand, the saturated unit weight, the width of the anchor plate, and same thing can be seen from these graphs that for all the different types of the flow conditions, the results are overlapping each other. These are the failure envelopes which show the proximity of the stress state to the yield condition. So these validate our previous statements which where we said that the pull-out capacity is higher when the depth of the water table is higher and when the shear strength parameters are higher. I have just added one slide which show the results in case of clay. All the other results were for sand. This is from one of my published papers, and it shows that in case of clay, there is the effect of the flow conditions on the pull-out capacity, like for evaporation and for infiltration. The results are varying. It is not like as in case of the sands. Coming to the conclusions from this presentation, we could see that the collapse load or the pull-out load of the vertical anchors, it is not affected much by the flow conditions. However, it increases with increase in the depth of the water table, with increase in the angle of internal friction of the sand, and with increase in the depth of the embedment depth of the anchor plate and the width of the foundation. And the yield zone, it is larger for higher values of depth of water table and the angle of internal friction of the sand. Thank you.
Yeah. on time. Spare time for one question at least.
Thanks for your sharing. Actually, because your anchor is send your conclusion that the water table is not really affecting the performance, which is quite a contradicting with our construction experience. We have some projects which send the high water table because got a lot of problems.
Yeah, so it is not that the water table does not affect the pull-out capacity, as we can see that the water table is on the x-axis and it is changing. The pull-out capacity is changing with the change in the water table. What does not change is the pull-out capacity with the change in the flow conditions, the evaporation, no flow, and the infiltration, not the water table.
Oh, okay, thank you.
Yeah.
The flow condition is very difficult to check.
Yeah, please, you can actually interact with her a little later. But I have a follow-up question. Because most of these cases, if you have sandy environment, the very high permeability will take off your suction. So do you see any effect of suction on the pull-out capacity? It shouldn't be generally.
Yeah, so actually from this equation, we can directly correlate the permeability with the suction stress. Like there is this equation, this term which
is it designed or derived for clayey soils
no,
or
it
sandy
is for
soils?
all types of soils, because here different parameters are alpha and Ks, which is this hydraulic conductivity. It is different for different types of soils. So it is, this equation is valid for all types of soils. So
Okay.
from here we can relate the hydraulic conductivity with the suction stress and then directly to the pull-out capacity of the anchors.
Okay, sure. Thank you so much.
Thank you.
Then we'll go to the next presentation. We'll go in the order now. Deep soil mixing with steel inclusion for 10-meter excavation support by, you're presenting. Okay. So, Leong? Mr. Leong.
Okay, good afternoon. First, thank you very much, Professor Suresh and Professor Sayed. Good afternoon, everyone. My honor to share our experience on the excavation support is deep soil mixing. Okay, yeah. This is a project in Malaysia. The actual project is a nice Soho, with small office, small home office model, 14 floors building with 2-level basement. Yeah. Let's look at layout. Is about 70 by 70 meters. The surrounding, all surrounding four sides are road. Then in the conforming design, the clients use CBP wall. CBP wall, you know, the power construction can be quite troublesome. Also need to do a lot of testing. So after we look at the soil profile, surface is formed to stiff clay, followed by formed to stiff to hard soil. Look at soil, not so bad. Yeah. Okay, so after a few discussions and analysis, we decided to use the deep soil mixing to support the excavation. This northern side length is 74 meters. The depth is about 10 meters. This western side, 69 meters. This is also the public road. Yeah. We have used 4 types of deep soil mixing. Type 1, because this space is very small, only about 3-4 meters. So for 10 meters excavation, 3+ meters is not sufficient to build up gravitational retaining wall. So in this case, we add steel inclusion in the wall. But of course, we had a discussion, where should we put the steel? There's a question. Of course, it's similar to a beam model, but in this side, it's more realistic to take the tensile force. Yeah. This side also the space is very narrow, also with the steel inclusion. Right on this side, We have enough space to build up gravitational system, so no steel inclusions required. Okay, for this one is quite simple model. For all the geotechnical problems, actually the criteria are quite similar. One is the stability, make sure it is safe. Another one is look at the performance. In this case, the main issue is the lateral movement. Yeah, the client allow us to have 60 millimeters lateral movement for just 10 meters excavation. So that's our design criteria. Of course, because surrounding has a road, also some buildings at a certain distance, we have done quite a lot of monitoring, building monitoring, groundwater table change, lateral movement, especially for the wall deflection. We have installed quite a lot of inclinometers. Yeah. Let's zoom in to just show the type 1. Yeah. This DSM wall at this site is only 3.4 meters. This one we include a little bit. We want to make sure they won't be kicked out. The deep soil mixing can be quite strong. It can have an unconfined compressive stress of about 1 megapascal. Yeah. But with that, we worry about the soil not strong enough can be kicked out. So these 3 rows, the shallow depths, just below the excavation level. These 3 rows, the full length from the surface to the bottom, with the steel inclusion here. We don't go very details. The bottom will be 3 meters. Yeah. Simple analysis has been done. Use hand calculations. Also, this one shows a simple practice 2D analysis to check the deformation and the stability. Basically, this model is very simple. You install the strong block here. You have steel inclusion, so the failure slip will be below this block. Yeah. Of course, we need to make sure this block itself has enough internal stability. Yeah. Don't let it collapse. If this body is strong, the failure slip will be here. It's quite simple. Yeah. In this case, we don't have sand, fortunately. Otherwise, the water table drawdown will be the problem. Yeah. Factor safety, enough. Usually in Malaysia, we design for permanent structures to have 1.4. Temporary structures, permanent 1.4, temporary 1.2 factor safety. Yeah. These 2 pictures show the construction in progress. I use the API TM22 rig. Just to highlight in this case, because the soil quite stiff, the moist content is low. For deep soil mixing, actually it's not so good. For deep soil mixing, the better one is that for clay with moisture content close to the liquid limit, which is easy to mix. Because this soil a little bit too dry, we add some water to cure the soil. So first cycle we go down, just with water, add water inside, yeah, to cure the soil. Then second round we add the soil cement grout. Yeah. This picture shows that steel inclusion push into the DSM. Usually we do it second day after the deep soil mixing. When it's not so hot, it can quite easily be pushed into the DSM column. Yeah, this picture shows the soil quite stiff, and even we add some water to cure it, it's still very dry. Yeah. Okay. So of course for the quality check, after installation at certain days, we call the sample to the lab test to see how much the strength can be achieved. In this particular case, we have got 36 samples. You can look at this. I just showed this one from the highest to the lowest. Lowest, you look at about 90% has passed the 1 ampere UCS, so which is considered. Okay, yeah, thank you. The highest is very high. That's the challenge of the uniformity of the construction. Yeah, shows construction done, the excavation done. We are looking at the results every week to make sure the movement is acceptable. Yeah, yeah. Some inclinometers, most of them are okay. Predicted 42 mm. This 29 mm good. This good. However, this corner almost reached the 60 mm. But because this for the power cap construction, they have trimmed this DSM, so that it's 3 meters trim, about 300 mm, which cause some more movement, I think. Yeah, that's all good. Okay, so just quick summary that this DSM would be a quite good alternative solution to DO or CBP. Yeah, if the space is enough. It's slightly less, you can add steel inclusion to compensate there's not enough width. Water cooling can be important in some cases, so it's very dry. Yeah, with this, I did say thank you.
Thank you so much. One question if you have.
Yeah.
Hi, good afternoon. I'm curious to know if there's a required like a specialized drilling technique in order to retrieve like good samples for you to get for use for unconfined compression test. Because I'm just concerned if you just use a like simple coring, you'll never get good samples for coring for testing.
Yeah, we have two types. One kind you can use a coring the sample, something like a low coring to get a sample to a lab to the compression test, check the strengths and the modulus. Another one you can get this sample, which is much cheaper and convenient. Yeah, thank you.
Thank you. Thank you so much. We have a next speaker, a study on the minimum required cohesion for retention of soil in excavation using soil nailing systems by Professor Satyanarayan Reddy. 7 minutes. I'll raise my hand at 6 minutes.
Okay,
Yeah.
okay. I'll try to be quick. Any volunteer is there? Make it full screen. It is not happening. Symbol is different. Huh? Yeah. So, good evening to all of you. So, I am going to present a paper based on my scholar's work on revisiting of required cohesion for stability of soil nailing. So as all of you know, soil nailing is a technique of reinforcing in situ soil by regular arrangement of closely spaced steel bars to form an inherent coherent gravity structure so as to improve shear strength and restrain its movements. So generally this soil nailing technique we will use to stabilize existing steep slopes or whenever we make excavations for creation of cellar, subcellar floors in the urban area. Generally, the most resorted technique for soil retention is soil nailing. So generally these nails are installed down the slope or excavation at an angle of 10 to 15 degrees with horizontal. Mainly the stability of soil nailing system depends on the shear parameters of the soil into which nails are being introduced, mainly soil cohesion and angle of shearing resistance. So most often you will see while excavations that are supported by soil nailing, either driven or grouted nail system, you will see sliding of soil mass along with nails. So that happens generally when you do it in sandy soils containing very low Kozu strength. So whatever 7 kilonewton per meter square that is specified, sometimes it is posing problems whenever depth of excavation is more. So an investigation has been made. So in our Andhra University campus we have presence of silty clay sand. So and the area surrounding Andhra University, many constructions are coming up and we have witnessed such failures of sliding when people were trying to stabilize, particularly when they are excavating beyond 6 meters or so. So that's why this study has been taken up. So the properties of soil from our campus, based on gradation plasticity characteristics, it gets classified as SCSM, and it has a cohesion of 8 kilonewton per meter square and angle of shearing resistance of 31 degrees. So for the analysis sake, we have formulated a simplified method. We did not follow Gassler method. We have coupled the failure plane that will be considered in internal stability analysis of reinforced retaining walls. So soil nailed excavation, soil excavation slope and RE wall more or less will have similar behavior. Reinforced earth wall, you are constructing and retaining backfill. Here, as you excavate, you are introducing system, and finally it is becoming like a retaining wall. So that's why we have adopted a failure envelope of reinforced earth retaining walls from coherent gravity method, wherein the failure or rupture surface is considered to be inclined in the bottom and up to half the height of the retaining wall, and thereafter it becomes vertical, right? So and the vertical rupture plane intersects the surface, ground surface at 0.3 H. Even Gassler reported such two planar wedge surface failure in respect of cohesionless soils. In case of coso soils, rupture plane is reported to be circular. So based on that, that failure surface has been adopted, and accordingly, in coherent gravity analysis, the variation of coefficient of earth pressure is considered to vary from earth pressure at rested surface to a value of Ka, right, starting from surface to a depth of 6 meter, and beyond 6 meter it is considered to be active earth pressure coefficient. So as you know, we will be checking for stability of nails for safety against tension failure and pull-out failure. So the tension induced in each level of nail has been calculated using this formula, wherein we take horizontal stress acting on reinforcement consideration, and we multiply with area of influence of that nail. So that way tension is calculated, and factor of safety against tension failure will determine as the ratio of tensile strength of reinforcing bar by tension induced. So as per Federal Highway Authority guidelines, the minimum factor of safety against tension failure should be 1.8. Similarly, pull-out failure also we will check by calculating the pull-out resistance mobilized on the anchorage length, the portion of nail extending beyond the rupture plane. We calculate the mobilized frictional force, so expressions are given. So simple concept, normal force acting on the nail multiplied by tan delta, right? So if it is driven nail, it is gamma times Hj is overburden pressure, pi dl is circumference. So you are multiplying that with coefficient of friction. In case of grouted nail, the surface area of bar in anchored portion, you are multiplying with bond strength. So we will have to determine factor of safety by dividing float force with the tensile strength, tension induced in the nail, and it should be more than 2. So following these simple formulations, the designs have been made for driven and grouted nail for excavations having depth from 4.5 to 10 meter, considering a surcharge of 24 kN per meter square. Normally we consider whenever a roadway is passing adjacent to your retaining wall or your deep excavation. So 2 meter high surcharge road we will consider. So designs have been done with and without consideration of surcharge, and a phase batter of 10 degrees has been considered for the analysis. So driven nails of 20 mm dia with nail inclination of 10 degrees spaced at 0.5 meter. Both horizontal and vertical spacing have been considered. Coming to grouted nails, 20 mm dia nails with in a drill hole of 100 mm diameter with 1 meter spacing in horizontal and vertical directions have been considered, and a bond strength of 100 kPa has been considered. So initially for preliminary stability analysis, the length of nail is taken as 0.6 in case of 0.6 in case of design of nailing system without surcharge, and 0.7 where there is surcharge, and subsequently the nail lengths have been revised to satisfy the stability requirements against pull-out and tension failure. So these are the design summaries. So having worked out the design requirements both for driven and grouted nailing system with and without surcharge, we have carried out numerical analysis using Plaxis 2D software. So 15 node elements have been considered, and soil is taken to be hardening soil. Nails are considered as embedded beam elements, and facing is treated as a plate element. Medium mesh, that is triangular shape one, is considered. Poisson ratio is considered as 0.2, and the modulus of velocity is listed there. And the soil interface reduction factor, right, for adhesion factor and interfacial friction angle determination, this factor of 0.75 has been used, and a fascia slab of 100 mm thick shotcrete is used. So if you look at the horizontal displacement of soil nailing system for driven and grouted nails with and without surcharge, you can see that without surcharge, driven nailing system has indicated lateral displacements within 0.1 times of depth of excavation. Coming to grouted nailing system, it was okay up to 8 meter depth of excavation, but at 10 meter it failed. Coming with respect to surcharge, soil body collapse was observed. I'll conclude, almost over. So you can see from here, these are the 2D Plaxis analysis outputs. So having seen that it is failing mostly under surcharge loading condition, we have extended study revising the value of cohesion to 8, 9 and 10. So with the value of cohesion strength of 10 kilonewton per meter square, we have obtained for grouted nails as well as driven nails lateral displacements within 0.1 times depth of excavation. So you can see from 2D Plaxis output, there is no soil body failure and displacement up to limits.
Thank you so much.
Thank you.
Yeah, we can interact with him a little later. Yeah, sorry for that.
So I consider fortunate for chairing on 7th the same theme session, and today I am presenting a paper on behalf of my scholar. So thank you all for
thank you, sir. Yeah, we'll move on. The next presentation will be by Mr. Mahendra. Yeah, okay. So parametric analysis of anchored diaphragm wall supported system for deep excavations.
Very good evening everyone. My name is Mahendra and I am a research scholar from IIT Guwahati, and I am going to present my work on parametric analysis of anchor diaphragm wall support system for deep excavation. Deep excavation is often used in the construction of basement, underpass, tunnel and foundation, and the ground deformation are the major concern which is associated with this kind of excavation. Excavation cause soil unloading, which may induce local yielding, and if this opening is deep enough, if it can form some kind of shear surface, which result in some kind of shear failure. And to mitigate this effect, it is very much crucial to design and implement an adequate support system. So the challenge in my work is to design the anchored wall system to limit this formation while maintaining the adequate factor of safety. So for the analysis, 2D pre-and numerical analysis has been considered using Plexus 2D, and after carrying out the domain analysis, the lateral extent of the domain has been extended to 10 times the height of excavation from the wall, and 3 times the height of excavation from the bottom of the final excavation level. And after carrying out the mesh convergence analysis, a medium mesh has been adopted, which results into 2050 elements and 16,857 nodes with an average element size of 2.442 meter. To model the soil behavior, a hardening soil model has been used. Before going further, the validation study has been considered in the deep excavation case in the Berlin sand, which is basically 16.8 meter deep and 60 meter wide. And this excavation is supported by the 3 level of anchors with 0.8 meter thick and 32 meter deep diaphragm wall. For the comparison, a lateral wall deflection plot and the anchor force has been included, and both of them are in good agreement with the reference solution. For my present study, after the validation, the same numerical model has been carried out for the brief parametric study, which involved the following variable, in which first is HT by HE ratio, basically total height of wall to the excavation depth ratio, anchor inclination angle, anchor pre-stress force, and anchor longitudinal spacing. The anchor pre-stress force has been varied as a percentage of anchor ultimate capacity, which is calculated by considering the adequate factor of safety in the design load, and the design load has been calculated from the apparent earth pressure diagram given by Terzaghi and Peck, and the horizontal wall deflection, the sole parameter which is being evaluated here. So the aim of my presentation parametric study is to identify the optimal anchor wall configuration and to propose the equation to take the maximum wall deflection based on this aforementioned variable. The construction steps involve the excavation up to 0.5 meter below the anchor level and the dewatering up to 0.5 meter below the excavation level till the completion of the final excavation. So this slide summarizes the important result in discussion. So increase in the anchor inclination angle, decrease the anchor traction forces, which result in the increase in the maximum wall deformation, and with increase in the HT by HE ratios, there is a decrease in the wall deflection. And increasing the pre-stress force and longitudinal spacing will not help to reduce the wall deflection after a certain optimal range. So the table summarizes here, give you a different choice of optimal wall configuration based on the anchor pre-stress force, anchor longitudinal spacing, HT by HE ratios, and anchor inclination angle. In all of the optimal configuration, the factor of safety is well above the required minimum value. So based on total 144 configuration has been analyzed, out of which 110 simulation has successfully satisfied the safety and serviceability criteria, and based on the multi-variable linear regression, equation has been proposed to calculate the maximum wall deflection based on which contains all the variables. So concluding my presentation, so increasing wall penetration depth and reducing inclination angle significantly minimize horizontal wall displacement, and anchor inclination angle plays a critical role in governing both wall deformation behavior as well as the sensitivity of the support system. Larger longitudinal spacing leads to significant increase in wall deflection, and the combination of the combined influence of anchor spacing and pre-stress force is strongly govern both the magnitude and depth of wall deflection. These are my references. Thank you.
Thank you, Mahinder, for keeping it in time. Time for one question, if you have.
Yeah, I supposed to be asked about. You referred the PEG diagram, correct? The pressure distribution diagram. Anyway, you are using the Plaxis software. It is giving the pressure distribution, correct? That means what is the reason you use the PEG diagram?
Sir, actually, in most of the literature, they have following this Terzaghi and Peck apparent earth pressure diagram. So,
but that you are used for the validation or?
To start with my study, I have not compared both diagram, but to start the study, I have used whatever is in the literature.
Okay. bypass. Just understand, okay, if you are doing any references, please compare with your result. That will be better to understand.
Sure,
Thank you.
Thank you so much. Yeah, we have a next presentation by Dr. Aniruddhan, deep excavation in weathered rock profiles.
Thank you, Chair, and good evening.
Thanks.
Yeah, I must thank my co-author, Mr. Madan Kumar from Keller, and I thank Geotech Asia for this opportunity. I will talk about some experience we had in the case of deep excavation in weathered rock profile. So this will be the sequence of my presentation. Project site, briefly I will discuss, then geological conditions, and what we executed for this 15.6 meter excavation. And we had a failure because of floods. And I will briefly discuss what could be the root cause for the failure and what restoration steps we took to regain the excavation, then some concluding remarks. This is the site and the project layout. You can see the project is a corporate office construction with 4 basements, ground floor and 10 floors, and the plot size is approximately 2,300 square meters, and the wall perimeter of the basement wall perimeter is about 200 meters. We do not have any heavy structures around, but we have very busy roads on 2 sides. Means most of the roads are always busy with heavy traffic. And this is the profile, geological profile we have in the site. It's a very small thickness of backfill, and weathered disintegrated rock for 3 to 6 meter thick, followed by weathered, very severely jointed rock, probably grade 5, which extended up to 18 to 20 meters, and followed by grade 4 weathered rock. Excavation depth was 15.6 meters. So the executed design is something like this. We had secant pile wall, which was only up to 14 meters, while the excavation depth was 15.6 meter, and we had one level of anchors and corner studs, then another level of another set of anchors and corner studs. You can notice that there is no anchors in the corners. Only the anchors are in the middle portion, and corners are supported by the corner studs. We have to notice that corner is very obtuse with 136 degree. Actually, that was the reason for the failure. And they also put benching after 11.5 meter for about 1.2 to 1.5 meter to add stability to the short pile lengths, thinking that it will add to the stability. This is the constructed excavation retention system. They excavated up to the final level, put the PCC, and then construction was about to start. And unfortunately, we had a incessant rain and high flood condition, and part of the retention system collapsed. We had 4 fatality, then we had property damage. So these are some of the pictures of what the failure condition. We have this corner stud failed and anchors failed, which pulled the road also, part of the road also into the excavation. You can see all the piles were toppled because there was no enough toe restrain, even though they provided a benching. you can see that very interestingly there is no groundwater, despite very high rains, very heavy rains and flooding. So we presume that the failure was due to flood water, because flood water height was about 1.5 meters, and which means the system did not have enough factor of safety even with the high water table or any flood conditions. So we understand that the possibilities are of failure are, one is because of the design was not done for shallow groundwater conditions, and if it was designed for shallow water conditions, it had enough factor of safety against flooding also. And the obtuse angle of 136 degrees led to very poor strut action, which led to the initial failure. The further failure of the anchored portion pulling out the road. Then the benching in the grade V rock was not effective, because of which the piles toppled into the excavation. Now restoring was very tedious job. We had to reclaim part of the excavation with manufactured sand, which was dumped into the excavation. But by the time we started doing this, the groundwater raised up to the ground level. So the filling was done in just water, just dumping the soil, and which was used for as a platform for further restoration work. We used 1 meter diameter continuous pile wall. We took these piles to 22 meter depth, which is about 5 meter below the excavation level. And to restore the road, we had to compact the sand. So we used sand compaction piles to compact the sand confined by these piles and the undisturbed soil beyond the failure point, and the road was restored. And we also used anchors at 2 levels for supporting the continuous pile wall. To add the stability of the existing system, we added one more strut at the middle level at 7.5 meter for the entire area. In the conclusions, what we see that failure provided a good opportunity to understand, but with very high cost of restoration. And it is better to adopt safe designs than to pay for failure. Groundwater surprises must be always anticipated. Critical junctions like corners with obtuse angles need more detailed analysis, probably with 3D analysis. And the success of retention system lies in safety, resilience, and strict adherence to no-go rules in the design. This is the usual practice by Color India, so I have to support that way of design. Thank you very much. I invite everybody to Chennai for IGC 2026 in next December. Thank you very much.
Thank you, Mr. Anirudhan. I think you're a little emotional. Yes.
Yeah, according to the Indian law, is it permissible to go into the other adjoining lands in these ground anchors?
No law allows that.
Then,
but
in case it is going to the adjoining
they do it. It was not my design, but I intervened only after the failure. But many people take that for granted and go to the adjoining land.
It is not legally allowed.
It's not legally allowed.
Maybe at least some permissions have to be taken before this kind of things happen.
Thank you.
I hope, you can interact with him during the break or, Thank you so much. So we'll go to the next presentation by Professor Sawant Sweta Singh. Numerical study on axial load capacity of group of granular anchor piles embedded in sandy soils.
Okay, good evening, everybody. Myself, Shweta Singh from IIT Roorkee, India. I'm here to present my work on numerical study on axial pull-out capacity of group of granular anchor pile embedded in sandy soil. These are the contents that I'm going to cover one by one. Starting from the introduction. So, with the rise in the population, there's a rise in the demand for civil engineering structures like transmission line tower, multi-story building, overhead storage tanks, or the tall chimneys. So, what happens? The foundations generally the foundations are required to transmit the compressive load safely to the subsoil. But sometimes these compressive forces accompanied with the movements due to the lateral forces, resulting in the overturning or the upliftment of the foundation. So, however, the pile provides a justifiable solution to such issues. But the challenges occur when the supporting soil medium is a weak subsoil deposit, just like loose sand deposits, collapsible soil, or expansive soils. So what happened? The poor subsoil deposit resulting in low bearing capacity and excessive total or differential settlements. However, there are some available methods that have been used in cohesionless soils, such as vibro-flotation technique, dynamic compaction, blast compaction, compaction by pile. But the limitations are like these methods require efficient labor, special machinery and equipment, time consuming and high construction cost. So Fanny Kumar, 1997, he introduced the concept of having the compressible pile to resist the pull-out load with minor modification in a conventional stone column or the granular pile, which is commonly known as granular anchor pile. Coming to the background of the granular anchor pile, as Fanny Kumar in 1997 said that there is a slightly modification to the conventional stone column. So what happened? The anchorage is provided through the mild steel anchor rod that is attached to the anchor plate at the bottom, and it is cast monolithically to the footing at the top end. Generally, the granular material that we use in the granular anchor pile is a mixture of locally available crushed stone aggregate and a coarse sand. So during the tensile force or the pull-out force, sorry. The uplift resistance is mainly derived from two things, that is the friction, mobilized friction along the pile soil interface, and the self-weight of the pile footing assembly. So few of the authors like Kranti Kumar et al. 2016 and 17 and itself Kumar 2002, they have documented that granular anchor pile is very effective and economically ground improvement method, improve shear strength properties of the soil and increase uplift capacity of the loose sandy soil. So the first part of the work is the numerical validation of a field experimental study done by Kumar 2002 on a group of 2 GAP embedded in cohesionless soil. The details of the experimental study is like the diameter of the pile is kept as 0.3 meter, length is 6 meter. Configuration is group of 2 piles, granular anchor piles. The depth of the groundwater table in this study is like 6.2 meter below the ground surface. So in the modeling consideration, the plant emission is kept 20 times the diameter of the pile according to the Robinsky Morrison 1964 and Kishida 1963. The depth is taken as 1 meter below the pile length. The spacing is taken as 3 times the diameter of the pile. The soil volume and the pile are modeled as the volume element. Anchor rod is modeled as node to node anchor. The thickness of the anchor rod is taken as 0.0317 meter. So for the tensile load, a uniform prescribed surface displacement has been applied on the top of the footing plate in the positive direction, that is the upward. So Moore Coulomb criteria model is used to define the constant relation for the volume elements like soil and pile. To simulate the real field condition, standard fixed conditions are applied to the geometry model. These table 1 shows the material properties for the soil and pile material. The properties of pile material are taken from the Rao 1982. Table 2 shows the material properties for the pile components like base plate, footing plate and the anchor rod. Figure 5 represents the comparison of the field test results with the numerical model for a group of 2 granular anchor pile. So here Kumar 2002 determined the uplift pull-out capacity by 2-point tangent method that is plotted from the curve between the uplift force and the upward displacement and reported at 170 kN. So a similar approach is adopted here. That is obtained from the Plaxis model to determine the pull-out capacity and is found to be approximately 165 kilonewton. So the second part is like the effect of the ground water table level. So in the first case, the groundwater table was at 6.2 meter below the ground surface. Now, if we increase the groundwater table level like 3 meter and to the surface level, what happens? So here, figure 7 shows the ultimate pull-out capacity for the variations of the groundwater table. Here we can see that on increasing the groundwater table, or if we move upward to the ground surface, the ultimate pull-out capacity decreases. There is a percentage reduction in the uplift capacity from 15.15% to 21.42% as we move upward to the ground surface. So this might be because of there is a reduction in the effective stress and so the shear strength of the soil. Second is the effect of a group of 3 granular anchor pile. What if we add instead of 2 granular anchor pile to the group of a 3 GAP? So what happened? So here figure 8 shows the comparison of uplift capacities for a group of 2 and 3 GAP. Here we can see that as we increase from the granular anchor pile from number 2 to number 3, and so here the uplift capacities of the pile increases, and the group of 3 granular anchor pile are the configuration is like equilateral triangle. Yes. So from this table 3, one more thing is to be noted here that however the uplift capacity of the pile is of the group of pile increases on increasing the number of pile, but the efficiency decreases. This might be due to the interaction or the overlapping of the pressure bulbs under the soil. Coming to the conclusion part, so a numerical model for the GAP is validated with the experimental study of Kumar 2002 using the FEM-based software. The pull-out capacity of the group of GAP reduces with the rise in the groundwater table. The highest resistance to the uplift force is obtained as 165 kilonewton for the groundwater table 1, that is like 6.2 meter below the ground surface. Furthermore, as we increases the groundwater table level from 3 meter to the surface, the pull-out capacity decreases from 140 to 110 kilonewton because of the loss in the shear strength of the soil. The last is the efficiency of the group of the pile decreases as the number of pile increases from 2 to 3 on the virtue of interaction effect. This is due to the fact that for the given upper displacement, the pressure bulb for the individual pile overlaps and result in the reduction in the uplift load carrying capacity by the individual pile in the pile group. Here are the references. Thank you so much.
Hello, thank you very much for being on time. Is there any question for her? Yeah.
Thank you, very good presentation. Just one question, this foundation system is for expansive soil, I believe so.
Yes, sir.
So did you also try to model that infiltration induced swell pressure that will come on the GAP?
Okay.
Either by numerical simulation or as an indirect form of an increased swell horizontal pressure or something like that.
Okay, so firstly, this is the validation from the Kumar 2002 study. So the soil he used in his experimental study was sandy soil, right? So there is no like expensive soil, the swelling pressure coming in the sandy soil. Okay, now if we model it in the expansive soils, right? So see, what we can do is in Plaxis, we can apply the volumetric expansion laterally or vertically. So by that method, we can induce the swelling pressure.
So currently they focused on only the anchor region only.
Anchor region only in a sandy soil, yeah.
Adjacent clay is not modeled.
Yes, yes.
Great.
Thank you.
Okay, the next presentation is trench stability in construction test of diaphragm wall with enlarged part by Akihiro Iwata. See, not here. Okay, then we'll move on to the next one. Performance of sand tire derivative mixture as a compressible inclusion behind retaining wall. Is somebody here? Okay, then the next after that one is numerical investigation of normal and elasticized geoform inclusion behind a rigid yielding wall. Yeah. By Dinesh Bishnoi.
Sorry.
From the top, bottom left button is not there. Slideshow from the beginning.
Okay, I'm not aware about that.
I think this is some another office version.
Okay. Good evening, everyone. So my name is Dinesh Bishnoi. So I'm going to talk about mainly about some product called as elasticized geofoam. But I will compare it one more product which is from which it is derived, that is called virgin or normal geofoam. and we are checking its efficiency behind a retaining wall, how its performance through numerical modeling. So first of all, there are several retaining structures which are used, and so it is mentioned here. So any structure which supports soils at two different elevations can be considered as a retaining walls, and some of the examples are this one. So these walls are designed based on the earth pressure. It is getting subjected from the backfill and traffic, even earthquake also, and the dimensions are proportioned accordingly. If we somehow reduce this pressure on this wall, then what happens? It achieves reduces maintenance cost, and in some cases it can reduce the section dimension also. So I will be primarily focused on the reinforced concrete walls, so which are rigid and yielding walls. There are solutions available like relief shells, replacing the whole material, or providing an inclusion material between the wall and the soil. So what is happening? There is a wall. When we are placing a compressible material, instead of wall movement, the compressible material will compress, and because of that the soil state will change in the soil from at rest to active. So people I will be focusing on that only. And for our inclusion material, we have used geofoam, which is scientifically called expanded polystyrene. So it is like a thermocol type of material. So there are several properties which make it a suitable material, construction material, and main thing is they have predictable stress strain behavior, and it is a manufactured product. It is environmentally safe. It doesn't generate leachate and everything. There are lots of studies has been done through numerical modeling, through physical modeling, and even by us also. We have performed field testing and numerical modeling, and what we found from the literature survey that when we are using normal material, the pressure is reducing on the wall in the range of 10 to 78% depending on the type of wall and the loading conditions. But there is one problem, not problem I will say, the issue with this material, because this is a manufactured product, so it has some cost, and which restricts its application. And what we found that the efficiency of geofoam depends on the thickness of the geofoam. So if and as the thickness increases, the pressure reduction increases. So there we did some literature review, and we found about some elasticization process. So suppose this is a normal geofoam. If we compress it and then remove the load, then it will become a totally new product. So that will be called as elasticized EPS or elasticized geofoam. So this is the cycle. This simple cycle of compression, recompression creates so much difference. If you see the behavior here, options, I have this highlighter. Okay, it's visible. Okay, so color I don't know actually how to say. So this is the behavior of normal geofoam. You can see that after reaching some certain extent, it starts yielding uncontrollable. And when we are designing the compressible inclusion with this, we make sure that our strain limit are within this %, and this is only 1%. But because of this cycle of compression and recompression, that behavior changes. Suppose if we are compressing this material to 66% of its initial height, then the behavior is this one. So it becomes highly compressible and shows linear behavior. So the strain requirement or creep problem can be avoided. And similarly, if we compress the material to different amounts, it will show different behavior. So we have control over the rigidity of the material. So that is not the case with the normal geofoam. Now we had done some field testing with the normal geofoam. So and also numerical modeling. So we have utilized this model and prepared the numerical model. So there we compared the performance of normal geofoam and elasticized geofoam. So this was the numerical model which we had done, and these are the constitutive model we have selected for all the materials: wall, foundation soil, backfill soil, normal EPS, and elasticized EPS. For all these 4 material we have validated and through literature. For elasticized EPS we have selected linear elastic material because in our testing the strain range was within elastic limit only. So for our case initially we have selected in a linear elastic material. These are the properties. And if we talk about results, so this is the behavior earth pressure variation along the depth when there is no material. So this is the control case. When we are placing the normal geofoam, So if we focus here on, this is there. So this is of EPS 15, that is the density of 500 mm thickness. Then this much pressure reduction is there. And when we are elasticizing this material, you can see here that that efficiency pressure reduction that we are getting with normal EPS of 500 mm thickness, we are getting it with around 100 mm also. That is 1/5 our thickness is reduced. On further increase, the pressures are reducing further. This we got from numerical modeling, and strain levels also varied. So this was the summary of the numerical model. This was a what we call not the in-depth study. This is in this conference we have only preliminary studies, and if we see the results here, what efficiency we are getting with normal EPS, that is 22% pressure reduction, we are getting with 100 mm, and if we are increasing, it is increasing up to 30% also. If we talk about wall deflection, because it is a yielding wall, it will deflect. So wall deflections are also reducing when we are increasing the thickness, and elasticity, if you see here, for 32% we are getting here, and compressive strain summary is also there. I am focusing so much on compressive strain because elasticized material behavior is highly dependent on the compressive strain it is getting generated. The major problem is creep. So from this preliminary study, I can say that elasticization can be an effective solution. It can reduce the thickness of normal EPS drastically without compromising the efficiency of the inclusion system. And also one good thing with EPS is that we have control over its stiffness. So if we compress it by different strains, its behavior changes. So that two things we have found, but there is limitations also because we primarily focused on the static study only. And as I mentioned, we have used a linear elastic, but it was having some plasticity also. But it was linear, but it is not linear elastic. There is some plasticity. For our study, we use linear elastic, so there more study is required for elasticized material to understand its mechanical behavior, damping characteristics, and its basically its efficiency for time-dependent loadings. So this was my presentation. Thank you.
Yeah, thanks Dinesh for keeping it in time and also highlighting limitations of this study. So next we have two more presentations. Mr. Chakrabarti? Yeah, sure. So design and construction of seepage barriers using plastic concrete.
Good afternoon, everyone. Myself Shantanu Chakrabarti, and today I am going to present one small project, which the problem we encounter inside, and how we handle in economical way. Actually, in the previous discussions in deep foundation, in deep excavation, we only concerned about the stability part, but in some cases, seepage is the major factor compared to stability. So in our problem, I will discuss how we encounter this problem and what are the material we use and how we design and what is the outcome after actual implication on the site. So the problem is that we are developing a pump storage project. For that, we have to go for a deep excavation to prepare a powerhouse. Powerhouse is what? From some water we store at the upper reservoir, and we drop the water at a particular defined head, and so that if we won't go a deeper powerhouse, we aren't able to generate lot of power. So that's why in our cases we had to go 60-meter deep powerhouse. Now the problem is that the site where it is located, the soil was like top few meter was overburdened soil, and other than that highly weather, and after that it is a moderately and strong rock was there. So the stability purpose is not a problem, but the problem was that the highly weathered and overburdened soil has poor in permeability purpose, means percolated a lot of water, and you can see that the excavation location is near to the water body. So what we did, we make a cut-off wall, but the cut-off wall was made of plastic concrete. Now the plastic concrete, maybe you know and maybe not know, because it is not that conventional practice. In plastic concrete, why we use plastic concrete? If we go the same process using rigid concrete diaphragm wall, in that case, two problems are there, as it is not huge construction cost. Second thing, when I am going to, there is no problem with the stability when I am going to use a rigid structure. So little bit of deformation create lots of bending moment and shear. We have to add reinforcement. But if you use plastic concrete, which is a ductile in nature, so what it do, when little deformation happen, it adjusts its position so that it overcome the other stability, local stability concern, and also plastic concrete is low in permeability, so it overcome the permeability concern. So in our case, we construct that plastic concrete wall using secant pile method. There is a diaphragm wall. How we develop diaphragm wall? Using a gravel, we excavate it, make a trench, and then we fill the concrete or any other material to fill the soil. But here, what we did using the secant pile method means overlapping piling, means, and so it reduced the time of construction, and the overlap was 250 mm. Now the basic ingredients for the plastic concrete is this gravel, sand, cement, and main key factor is bentonite and water. This cement water content is conventionally high compared to actual water cement used in the concrete, and the bentonite actually giving the plasticity, enhance the ductility, and significantly low the permeability, and you can see that it suspends cement particles and gravel, so that it helps to get a good ductile behavior. Now the problem is that there is no standard pattern or standard data is there. How much, what is the trial mix should be, how much we have to add, which proportion we go. So for that, what we did, we collected the data from the literatures, means what are the how much suppose UCS will cube strength they achieve for different moisture content, what is the permeability we achieve, what is the slump we achieve. Now the guideline is that in our IS code, the slump should be, if we use plastic concrete, the slump should be within 180 to 200. Now another concern is that you see that a guideline that our permeability should be within 10 to the power minus 7 to 10 to the power minus 8 cm per second, meter per second. Now the another thing is that how much UCS you are going to use. Now another factor we know that the plastic concrete, the elastic property, the elastic stiffness should be almost similar to the adjacent strata, so that if little deformation happen, so it behavior should be homogeneous with the adjacent strata, so that using the geological profile, we define the elastic modulus of the strata, average strata, and relations are there that if my elastic property is this, so corresponding this amount of cube strength we need. So our trial mix was defined accordingly, such a way that we know that this is the proportion initially literature has proposed, authors have proposed that this mix should be taken, and this is the properties are there. So we take such a way that this range, this particular range, like bentonite cement ratio should be like this, cement content should be like this, bentonite slurry, then sand gravel ratio like that. From the literature, we did the trial mix and got a suitable one, because why 1.51 we chosen, because this 1.51, if we convert the correlation to the elastic stiffness, it matches with the surrounding strata. So that way we find out the elastic modulus UCS value of 1.51, and this fifth number of batch is was suitable for our study. Now then we did the numerical analysis in present without cutoff. How much, sir? 1 minute. Okay, sir, I'm finished. Then we did the numerical analysis using finite element and find out the how much seepage is happening without cutoff wall and in place of cutoff wall. So we found out that if I go to the rock strata inside a 2 meter socketing rock strata, at least it's reducing the permeability 10 times. And then we set up the batching plant, and like here is the dry bentonite feed in the agitation tank mixture. Then we keep it for hydration for 24 hours to hydrate the sample. Then we load it in the hopper and do the piling at the site. Piles are like we did the 568 secant piles, and we do the numerous probe holes and also bore holes to see that whether we are getting the exactly required strata or not, because sometimes we encounter boulders also. So maybe in previous borehole study is showing us that it should go 12 meters, but we are at 10 meter or 5 meter we are terminating getting the hard strata. So that's why we did lots of probe holes and we achieved. And also the pile integrity test also showed that our piles are proper, and this is our successful outcome. We able to achieve the reach the 60 meter excavation with reduction of the seepage. You can see little bit was there, but we can overcome by pumping and storage. And now you are also become a part of this successful study.
Thank you so much.
Thank you.
Yeah, we are running out of time, so we'll move on to the next speaker. Dynamic response of circular footing and findings from experimental soil foundation interaction. Professor Fardi.
Yes, thank you very much. Good afternoon, colleagues. Hope you are not so much tired. The last paper of third day, so I have to. How can I get the USB? Oh, okay, here's which one? The E, huh? Oh yeah, this is that's. Oh, sorry. Yeah, this is my paper. Yes, this is my paper. I can play from here, huh? It's okay. Yeah. Close all. View slides.
Resume.
Okay. Let me. Okay. Okay. The title of my presentation is Dynamic Response of Circular Footing, Findings from some Experimental Physical Modeling Tests, Soil and Foundation Interactions. I'm Associate Professor in Sharif University of Technology in Tehran, and also the President of the Iranian Geotechnical Society. For this paper, I have had many colleagues. I mean, I have to appreciate my students, PhD and MSc students. Mr. Jafar Maleki was the MSc student that worked on this subject. This is the general outline of the paper, same as usual. I will skip it. The motivation for this research, which has been started maybe about 15 or 20 years ago, and it is continuing still, was that all the colleagues are familiar with the dynamic design of foundations. I mean, the coefficients that we are using for that, that they are available in the dynamic soil dynamic books. You have, I'm sure, familiar with that. But most of them are not so based on experiments and, how to say, experienced by the test. There is in literature some real scale tests. There is some numerical analysis for that. And of course, there is some limited physical modeling tests. So that's why that we choose this subject, and we have studied with various, how to say, subjects the determination of impedance functions using physical modeling. As you know, the impedance functions are the most important parameters which is used for the design of surfacial footings in dynamic conditions. For example, as for the literature, the research of Ni, 1987, is one of the research that was done for vertical dynamic impedance analysis on small scale test. As I mentioned, we have had started from 2006 this research, and different subjects and different parameters, vertical loading, horizontal loading, combination of both of them, effect of embedment, effect of shape of the footing, and also soil types, and various parameters have been applied in the physical test, which I'm going to present today about the effect of weight of the foundation footing and also depth of embedment. As I mentioned, yes, impedance functions are, the most important parameters, which is going to be the result of any test. Here you can see the general setup of the test. There is a box, 1 meter by 1 meter and about 1 meter depth. And also we had some shakers, horizontal shakers in one or two directions, you can see here. And the typical foundation mounted on the sandy soil, which you can see here, which will be more clear in the next slides. And here also cross section of the physical models I mentioned. And for simulating the foundation, rock foundation, we had used concrete blocks with different thicknesses for checking the effect of depth of foundation, depth of bedrock. So in this study, we examined the impedance function of circular foundation subjected to two-way horizontal loading under rigid base condition, as I mentioned. Of course, we had some instrumentation, accelerometers, soil pressure meters, LVDTs, and so on. And for preventing, because we had applied sinusoidal loading with these shakers for, isolating the model from the returning back waves from the boundaries, we had used thickness about 10 or to 15 centimeter thickness sawdust in the bottom and in the side walls of the model. Here is some details about the model preparation, which I'm skipping it. And again, we use kind of, as I mentioned, a uniform sand. Bubbles are sand, which is from the north coast of Khazar Sea in Caspian Sea, northern part of Iran. And we used air pollution method with the density of the models was about 50-something percent, 54%. Some pictures of the instrumentation, as I mentioned, different shakers, B and K shakers we used, and also instruments for the measurements, data logger, and so on. This is one of the typical foundations which was used as a model of footings from concrete. Okay, here you can see the general setup of this paper. Two shakers, horizontal shaker, perpendicular. They are applying the load, and co-phased horizontal loads were applied to the model, side view and top view of the shakers. And the details of the test, I'm sure that you can find the detail in the paper. If we go through the basic relations, we can show that there is a parameter kh could be related to the dimensionless frequency A0, which is related to the stiffness, and also ch, which is related to A0 also, and could be meant as a damping parameter. And in the most of the relations in the soil dynamics, you are seeing this. Okay, I'm going to conclude. So just two pictures. Here in this test, effective foundation embedment is shown. We had no embedment in some tests, and also one D to H. D is the diameter of foundation. H is the embedment, which was same as the foundation diameter, the embedment. The effect of embedment could be seen, and also this one. This is for KH with A0 and CH damping with A0. And another test, as I mentioned, effect of foundation weight. Foundations, concrete blocks, 2.6 kilogram or 4.3 kilogram, two types have been reported here. We can see again there is some change based on the weight of the foundation for different A0 or dimensional frequencies. Please, if you are interested, check the paper. But as a conclusions, the objective was assessment of dynamic response of circular footings under two-way horizontal harmonic loading. The method we used was the physical modeling test. Observations was the rigid base model sometimes showed complex, unpredictable behavior due to the wave propagation and reflection. Effect of embedment, higher embedment ratio increases dynamic stiffness and damping, as we saw in the graphs. And the mass of the footing, minimal effect on dynamic response. Some references, as you can see, and thank you very much.
I think everybody needs that coffee. Thank you so much.
Yeah. Thank you very much.
If you have one question, anybody has a question? Okay, thank you so much.
Thank you. Thank you, Mr.
Okay,
Chairman.
so thank you so much for all the speakers. I think we have one theme speaker, Professor Arvind Raman, and then we have 10 presentations in session. I think it's the last session. And thank you for patient hearing. And I'll conclude this session by presenting a memento to the theme speaker.
Thank you, Professor Siris, Chairperson Professor Syed. I would like to request our Chairperson, Co-Chairperson to give a memento to thematic speaker Professor
Sorry, I
Raman.
forgot to acknowledge my co-chairperson. Yeah, thank you so much for keeping the time. He was the responsible person who maintained the whole time.
I now request Professor Fardeen to present a memento to Chairperson Professor Siris and Co-Chairperson Professor Syed as a token of appreciation from the organizers. Thank you very much. Thanks.
That means your rock profile is 2 meters going up to 3 meters. Depth of excavation is 14 meters. So how do you do diaphragm wall and rock?